Good morning, everyone. My name is Pei-Hsuan. The two co-authors are my students. They love playing basketball. They practice basketball on a regular basis and participate in different kinds of basketball games during their college years. They were greatly motivated to conduct this study. Both of them had just graduated from the Department of Computer Science at National Zhengzhi University. So today, I will be the one to present our study's findings. The QR code I'm providing on this slide is available for everyone to download this video recording for your future reference. Even with a great interest in playing basketball, most modern people living in a fast-paced society actually have limited time for watching entire live basketball games or video replays. One NBA basketball game, for example, usually takes more than 2 hours, although it varies from one league to another. Even if basketball fans have time to watch an online live broadcast game or replay, they can easily get distracted during the game and miss some key moments in the game. After observing most NBA video clips from YouTube, we found that basketball game highlights are the parts that most fans want to see. Highlights refer to the shots that have been selected manually by visually assessing the footage. Therefore, it requires a lot of human labor and time to obtain. We also noticed that the video clips provided by the NBA are not always the actual shots made by a team, but rather fancy dribbles or rebounds made by the basketball superstar. Overall, the research purpose is to develop an intelligent classifier that can automatically identify the highlights of a live basketball game. Here, the intelligent classifier is trained to identify the video segments in which the scoreboard transitions from the basketball team's names to the team logos. The detection targets of the trained intelligent classifier are those scoreboard transitions. For example, in the game of the Denver Nuggets versus the Golden State Warriors, DEN versus GSW, within a few seconds of a shot, the team's name, GSW, immediately gets changed to its logo. These are other purposes of extracting highlights that we review from prior studies. We start to train the intelligent classifiers by preparing two datasets. One is the training dataset, and the other is the testing dataset. We adopted several approaches to prepare for the training datasets so that we can well train the intelligent classifiers. In the training datasets, we considered positive and negative sample datasets. The positive samples are the images or video segments that contained team logo images. The images could be displayed on the scoreboard or anywhere on the basketball court during the game. The negative samples are the images or video segments that are not related to the game, such as landscape photos. To better train the classifier, a prior study suggested utilizing the datasets related to the positive samples, such as the basketball court backgrounds, but without the detection target, that is the team logo images on the scoreboard or the scoreboard transitions from team names to team logos. Finally, we obtained a total of 229 video segments of shots as the positive samples that had the team logos on the scoreboard, and 787 images as negative samples, which were video segments without scoreboard transitions or unrelated to the game. As shown on the left side of the slide, these are the positive samples. The reason to place the team logo images anywhere on the basketball court is to prevent the classifier from detecting the team logo worn on a basketball fan's t-shirt or a hat during the live broadcasting within a zoom-in view. Instead, we intended to train the classifiers to detect only the team logo displayed on the scoreboard whenever possible. And the only chance to detect the team logo is in the middle of the basketball court and not in the spectator seats. On the right side of the slide, these are the negative samples. We used the Brisbane City view as an example of a landscape. In our study, we included other landscapes that were not related to the basketball games. Then, we pre-processed all the training and testing datasets in the following steps. First, we standardized all the positive and negative samples to a resolution of 640 by 480 and then saved those samples in BMP format. After that, we used object marker, which is from OpenCV, to identify the ground truth, that is the team logo. Then we ran Python codes to apply the SMOTE synthetic minority oversampling techniques algorithm to increase the number of positive and negative samples. During the data training step, we also use the hard cascade algorithm, which is OpenCV's pre-trained cascading classifiers, also known as the Viola-Jones algorithm, to detect multiple objects within a single frame in a hierarchical manner. More details about the approaches to identify hard features are provided in this slide. Hard features such as edges, lines, and four-sided shapes are rectangular features extracted from the input images and used to define bounding boxes for object detection tasks. Please note that in our study, only upright hard-like features, as opposed to the skew hard-like features, were used because the angle of the scoreboard in the video segments remains constant. This slide explains the differences between two different types of hard features. In our study, we use upright hard features. There are more types of hard features as shown at the bottom of this slide. There are more technical details that I cannot go over in this presentation due to the time limit. For example, how to denote positive and negative sample files, how to change the parameters for the variables, how to initialize OpenCV cascade classifiers, how to save the trend classifier in an XML file format, and how to combine all the highlight segments of a basketball game into one video clip by writing another set of Python codes. All these technical details had to be designed and implemented. Finally, we were able to train the classifier such that it might be considered intelligent and was capable of automatically detecting scoreboard transition from team name to logos. Here in this slide, the top 4 MP4 files are the original NBA video clips. After the trained classifier identified the highlights from the top 4 video clips, all the highlight segments were then merged as shown at the bottom of the slide from the left to the right, that is from clip.mp4 to merge 2, merge 3 to merge 4. To evaluate the performance of the intelligent classifiers, we employ two measurement metrics. First, we compare the time difference between the timestamps of actual shots by manually selecting the segments using a video editing tool, and the predicting timestamps in milliseconds identified by our intelligent classifier based on the detection targets. During a live broadcast basketball game, we confirmed that the intelligent classifiers was able to accurately identify the detection targets for the first 4 shots within 1 second of the actual shots. Another measurement matrix we used was the confusion matrix. Here, we only consider the accuracy rate and the precision score. First, the predicted highlights are the actual highlights that we are most concerned about. These are called true positive, TP. So, the ratio of TP out of all predictions is what we need to obtain. Second, if certain predicted highlights were actually not highlights, meaning they were false positive, FP, we had to know what percentage was truly positive out of all the predicted positives. Precision scores are commonly used in evaluating object detection tests, which is what we try to do. However, we did not pursue obtaining the recall or F1 scores because for a long basketball game, as long as the intelligent classifiers could predict and identify the accurate highlights and then merge them into one video clip, we consider it satisfactory for commercial use. We were not interested in investigating the predicted non-highlighting video segments that were actually non-highlights. The F1 score is the harmonic mean of precision and recall. Since we were not concerned much about the recall except precision, we did not further report the F1 scores. Certainly, all these scores can still be computed by using the confusion matrix. As a result, we obtained an accuracy rate of 0.64, and the precision score obtained by using our intelligent classifier reached 65.56%, which we consider to be a passing score. Overall, this study demonstrated the effectiveness of the intelligent classifier in capturing the scoreboard transitions and thereby the highlights of basketball games. Our intelligent classifiers can automatically extract the highlights of video segments during live broadcasting again. After merging all the highlights into a 10-minute video clip, basketball fans can enjoy watching all the shots made during the game. The classifier saves a lot of time and human labor required for video editing. Our study is beneficial for organizers to replay the highlight during game breaks. The shot scenes can also be used for basketball team promotion. For example, it is possible to generate traffic and views on a video platform. Meanwhile, it can help generate advertising revenue for both the basketball teams and the game organizers. One limitation of this study is that we trained the classifier to identify highlights narrowly defined as shots and excluded all other breath-holding moments such as steals or tricky passes, so future studies can consider extracting the highlights under different definitions in different contexts. The algorithms we employ in this study can also be replaced by other methods to reach higher accuracy rates and precision score. The references are listed here. Thank you very much for your attention.